Hello everyone. Let's wait for 5 more minutes for others to join and then we can start the session. I think we can start the session. It's already 3:03. So, am I audible? Can someone message on the chat box? Okay, great. So, is this screen visible? Okay, great. So, let me introduce myself. I'm Arpit Bal, and I'm a PhD scholar at IIT Bombay in the Department of Electrical Engineering. I'm also a recipient of Prime Minister's Research Fellowship. So, what we are going to do today is we are going to practice a few problems. So, I'll be solving a few problems related to the week 1 of digital circuits. So, I request you all to kindly take a pen and paper and also try to solve along with me. So, it will be helpful for your course as well as your assignments. Okay. So, for the week 1 lecture, so it was mostly related to number systems, and we will be solving problems related to that. Okay. So, let's start with the first question. So, the binary equivalent, so the binary number 101010 is equivalent to decimal number what? So, we need to find out the decimal equivalent of this binary number. Okay, so we have the number 101010. Okay, so what we can do is so just below the numbers you can mention their positions, and after that you can start with 0 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 into 2 to the power 2 plus 1 into 2 power 3 plus 0 into 2 power 4 plus 1 into 2 power 5. Okay, so this is 0. Next we have 2, then 0, then 8, then 0, then 32. Right, so we have 10 plus 32 equals to 42. Okay, so 42 in decimal, we can write it like this. Okay, so here the options are given, so 42 is the answer. Moving on to the next question. So the decimal number 76 in hexadecimal is, okay, let me admit other students. Yeah, so if anyone has any doubt, they can post it in the chat box itself, and I'll resolve that doubt. So within this session, so this session will be of 2 hours duration from 3 o'clock to 5 o'clock, and the recordings of the session will also be available. It will be shared by the NPTEL team. Uh, Even the slides will be shared with the participants. Okay. So now moving on to the next question. So we have the decimal number 76 and we need to find out the hexadecimal representation of that. Okay. So what we need to do is we take 76, we start dividing it with 16. So we know 16 fours are 64. So yeah, 16 fours are 64. So 4, and the remainder will be 76 minus 64, that is 12. Okay. So in hexadecimal system, okay, so if it is 12, then what we need to do is, so A actually corresponds to 10 in decimal, B is 11, C is 12, D is 13, E is 14, F is 15, right? So when we try to represent any number in hexadecimal, so after performing the long division, whatever is the remainder, we go in a reverse order to get the answer, right? So the first remainder was 12, the second remainder was 4. Okay, 4 in hexadecimal is 4, so let us write down 4. Okay, then 12 in hexadecimal we can use, yeah, so we can use this particular mapping to find out what is the value of 12. So 12 is C, right? So 4C is the answer. Okay. Moving on to the next question. So here we have to find out the binary equivalent of 45. So yeah, so there's a question from a student, what is hexadecimal? Okay, so hexadecimal is a form of notation, like you can represent the numbers. So there are various number systems, right? So one is binary, one is decimal, one is octal and hexadecimal. So in hexadecimal, what we do is, sorry Yashwant, I could not understand your doubt. Yeah, so in hexadecimal notation, this is how we represent the numbers. Okay, like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and after that we represent it with A, B, C, D, E till F. Okay, so moving on to the next question. Is my screen updating? Yeah, okay. So we have to find out the binary equivalent of 45. Okay, so regarding that hexadecimal part, so in hexadecimal, the value of each position is determined by whatever, let's say I'm writing something 3, 5. Yeah, the questions that we are practicing are some sample questions, and they will be helpful for you. So when you try to solve the actual assignment questions, and they will actually improve your understanding of the concepts that were taught in the first week. Okay, so yeah, so regarding hexadecimal, let's say we have a number represented in hexadecimal as 3, 5. So each place, what we need to do is, whatever number is mentioned there, so you mention that number into whatever is the index. So we start the index with 0, 1, 2, 3 and so on. Okay, so the index for 5 is 0, so we will do 16 to the power 0 in hexadecimal system, and similarly the next part is 3 into 16 power 1. Okay, just like in binary we do 2 to the power something, so in hexadecimal we do it 16 to the power something. In decimal it is 10 power something. Okay, so now moving towards the next question, the binary equivalent of 45. So let's do the long division method again. So for binary we will start dividing the number with 2. So if we divide 45 with 2, we will have 22 and the remainder will be 1. Then we again divide it with 2, then the remainder will be 0. Again divide it with 2, remainder will be 1. Again divide it with 2, remainder will be 1. Again divide it with 2, remainder will be 1. So we have to perform the division. So just a minute, someone is joining. Okay, so we have to keep on performing the division till we reach at a remainder which is less than 2. Okay, so here we can see we have arrived at the remainder, that is 1, right? So the answer to this is 101101, because we will proceed for the answer from a bottoms up approach. Okay, yeah, so we will proceed from the bottom of this solution. So we can see 101101. Okay, if you want to verify whether the binary value that you have obtained is correct or not, what you can do is you can back calculate. Like, 1 is 2 to the power 0 plus 0 plus this one is at a position of 2, this is at 3, this is at 4, this is at 5, right? So you can write 2 square plus 2 cube plus 2 power 5, right? 2 power 5 is 32 plus 8 plus 4 plus 1, that is 12. 13 plus 32, that is equal to 45. So you can re-verify your answers by again back calculating, right? Yeah, so we can move on to the next question. Yeah, so this was the answer that we obtained, 101101. Yeah. Okay, so the next thing is we are given a number and we have to find, okay, yeah, we have to find its hexadecimal representation. Okay, so this is the octal number that is given to us. We have to find the hexadecimal representation. Okay, so this is the octal number that is given to us. So let us try to write it in binary. So what we can do is for octal, yeah, for octal we will need 3 bits to represent any number. So the 3-bit representation of 1 in binary is 001, of 5 is 101, of 6 is 110. Similarly, for 1 it will be 001, for 2 it will be 010, for 4 it will be 100. Okay, now let us write it like this: 110, 101, 001, 001, 010, 100. Okay, now we need to find out the hexadecimal representation of this number. So what we can do is we can start grouping the bits in a group of 4. Okay, and as you can see, the decimal point, it appears after 001. So the grouping has to be done in such a way that we start from the decimal point and move towards the right if right of that number if we are if we want to group the post decimal bits, and we have to move to the left of that decimal if we want to like take care of the integral the integer value of that number. Okay, so let us group it in a bit of 4. Okay, so these are the 4 bits, these are the 4 bits, and these are the 4 bits, so we can append 3 zeros. Okay, so for the post decimal part, similarly we can do these are the 4 bits, these are the 4 bits, and then we can append 3 more zeros, and these are the 4 bits. Now what we need to do is the exercise that we performed just before 2 questions, that whatever number is present, we just try to write its hexadecimal equivalent. The same thing can be done now as well. So the hexadecimal of 1001, so 1001 is 9, right? So hexadecimal of 9 is 9. 1010 corresponds to 10. The hexadecimal value of 1010 is A. Okay, so then we have 0001, so 0001 is 1, right? Then we take care of the post decimal part. So 0010 it is 2, 1010 it is 10, so 10 is again A. Then we have all zeros, so all zeros we can ignore. Okay, so the answer is 1A9.2A in hexadecimal. Okay. 1A9.2A. Fine. So we can move to the next question. Okay, so then we are given a binary number, and we have to convert it into octal. So similar to how we did it for hexadecimal, even for octal we can do the same thing. So instead of taking 4 bits at a time, now we can take 3 bits at a time. Okay, three bits, 3 bits, 3 bits, 3 bit. Okay, so this is 010, that is 2, this is 1, this is 6, this is 6. Okay, 6612, and 6 in octal is also 6, 6 in octal is again 6, 1 in octal is 1 itself, and 2 is 2. So 6612 is the answer in octal. Okay, 6612. So far whatever questions we have solved, so does anyone has any queries regarding that? So you can type your queries in the chat box itself. Okay, so there is a question when to group in 4 and when to group in 3. So you group the bits in 4 when you are asked to convert in hexadecimal. Okay, so okay, I'll tell you the logic why we are going to group it in 4 bits. Okay, so the hexadecimal numbers, so they are from 0 to 15. So 15 is represented in F. So total number of unique digits are actually 16, right? So if you want to represent a 16 like a number like 16, how will you represent it in binary? If you want to represent a number 15 in binary, how will you represent it? It will be 1111. It means the maximum number of bits that will be needed is 4, right? So because of that reason, so we tend to group it in a group of 4 bits. So 4 bits is for hexadecimal and 3 bits is for octal. I hope that query is clear, Harsh. Okay, then we have another doubt. What are the rules of placing point while converting from binary to octal or hexadecimal and vice versa? Okay, so like I showed in the previous okay, let me go back to this point. Yeah, so here I'll tell you the logic. So what happens is any zero which is placed before an integer, it is not taken into consideration, right? So let's say while you are grouping 4 bits, right? And if you start from the very leftmost position, like if you start from here, then there is a possibility then that by the time you reach the decimal, you are falling short of a few extra digits to make it in a group of 4. So what we do is we start from the decimal towards the left side when we are moving for the integer part, and we move towards the right side while grouping, so that whatever numbers we are falling short of, we can append zeros to that, because after the decimal place, whatever is a zero, like after that particular number, it doesn't count, right? So we can use that for grouping of the 4 bits, right? I hope that query is clear, Sashwat. Okay. Okay, so then is there any other doubt that needs to be clarified? Okay, or else we'll move to the next question. So the next question is regarding, so let's say we have two n-bit binary numbers and they are added. So what can be the maximum number of bits of the output? Okay, so let us assume that we have taken two numbers. So yeah, Keshav, that's the correct answer. So when two n-bit binary numbers are added, the sum will contain maximum number of. So let us assume. So let us take two binary numbers. Okay, 1 and 2. So the maximum value for a 2-bit binary can be 1 1. Okay. So let us try to add these numbers. Okay, so we can see that the resultant number is a 3-bit number. Okay, so in this particular example, what we took is n is equal to 2. So it was a 2-bit binary. It is resulting in a 3-bit. So this experiment can be repeated for n is equal to 3, n is equal to 4, and by taking the maximum value numbers that are present for that particular n-bit binary number, and we can observe that the result is a n plus 1 bit. It can contain a maximum of n plus 1 bits. Okay, so from this observation, the option D is correct. Okay, someone raised their hand. Sorry, how I added? Okay, this is 1 1 1 1 1 and 1 is actually 2, so you will have a 0 here and a 1 in carry. Okay, then similarly 1 plus 1, it is 2 plus 1 is 3, so 3 in binary is 1 1. I hope that answers your query. Okay, yeah, sure, I'll repeat this answer. So I hope this question is clear itself, that there are okay, Harsh. Yeah, so yeah, so it is given that we have two n-bit binary numbers, and they are added, so what will be the like the maximum number of bits that can be present in the result of that addition. Okay, so for getting the maximum number of bits that can be present in that particular addition, what we need to do is we need to take the maximum value of those individual numbers. Okay, so for an n bit binary number, I considered n to be 2. Okay, so for a 2-bit binary number, what is the maximum value that we can have? That is 1 1, right? So what I did is I added 1 1 with 1 1, and the resultant was 1 1 0. Correct? Because it was 1 1 0, so it's a 3-bit representation, and we can show the same thing if we repeat with n is equal to 3, n is equal to 4, or n is equal to anything. We will obtain the result as n plus 1. So the maximum number of bits will be n plus 1 bits. I hope that this part is clear. Okay, if this is clear, then let's proceed with the next question. Okay, so this question is, find the sum of the following negative numbers represented in a sign magnitude 5-bit register using 1's complement. Okay, so we have two numbers, minus 1 0 1 0 and minus 0 1 0 1. Okay, so it said that we need to represent it in 5-bit register. So now we have only 4 bits. So let us append a 0 to make it 5 bits. 0 1 0 1 0 and 0 0 1 0 1. Okay, and here we are asked to use 1's complement form. So for using the 1's complement form, what we need to do is, whatever bits are present in binary, we just need to invert them, right? So for so for 0 1 0 1 0, we just need to invert the bits. It will be 1 0 1 0 1. Okay, so similarly for 0 0 1 0 1, we need to invert the bits. It will be 1 1 0 1 0. Okay, now we need to find the sum of these two numbers. Okay, 1 0 1 0 1 1 1 0 1 0. Okay, yeah, if you have a query, you can put it in the chat box and I will answer. Okay, fine. So what we observe is we have a carry at the output. Okay, so in 1's complement addition, if we have a carry at the okay, so the question asks us to do it in a 5-bit register. So here you can see, you can write it as minus 10 and minus 3. Sorry, not 3, this is minus 5. Okay, so we have the magnitude available with us, and we first need to convert it in the 1's complement form and then do the addition. Fine. So 10 is represented like this in magnitude, and 5 is represented as 0 1 0 1. Then what I did is I first made it into a 5-bit representation. So if you append 0 before any number, then the value of that number doesn't change, right? So that's what I did, because the question asks us to put it in a 5-bit register. So that's why I just appended 0 in both the numbers, number A and B, and then I converted them into ones complement form. Yeah, we need to append 0 because we need to put it in a 5-bit format. Yeah, for 10 4 bits are enough, but the question has asked us to represent it in a 5-bit format. Okay. Yeah, so as we have a carry, so in yeah, so what we need to do is, in ones complement arithmetic, whatever is the carry, so you just ignore it in this portion. You just take the main values. So let us take the main values, then whatever is the carry, you add it to the main value. Okay, so the final answer that we will obtain is this. Okay, so just a minute. Yeah, so this is the final answer, and we can see that we have a 1 at the at this position. So it indicates that the number is negative. Okay, the number is negative, and whatever value we obtained here, that is going to be the final ones complement value. So we can represent it like this: minus 1 1 1 1. Okay, yeah, so option B is our answer. Okay, then the next question is, so we are given a number and we don't know in which base it is represented. Okay, just like it can be octal, it can be binary, it can be hexadecimal, it can be anything. For this particular number, we need to find out what is the base of this number. Okay. Okay, so 110 x is equal to 132 in 4. Okay, so just like we do, whatever is the value at the last location, 0 into x to the power 0 plus 1 into x to the power 1 plus 1 into x square is equal to 2 into 4 power 0 plus 3 into 4 power 1 plus 1 into 4 square. This implies x square plus x is equal to 2 plus 12 plus 16. Okay, so by solving this equation, x square plus x minus 30 is equal to 0. So x square plus 6x minus 5x minus 30 equals to 0. This implies x square plus 6x minus 5 x plus 6 equals to 0. Okay, so we have x equals to 0. This implies x minus 5 into x plus 6 is equal to 0. So we have two values. X can be either 5 or -6, but -6 doesn't make any sense, or means base cannot be minus, so 5 is our answer. Okay, so moving on to the next question. So we have to find the equivalent of the 6-bit binary number that is represented on your screen, 101.101. Okay, so the same. Okay, so for any value that is represented after the decimal, what we do is we start with minus to the power the position's value. Okay, so towards the left we used to do it in positive. We used to start from 0, 1, 2. Towards the right we will start from -1, -2, and so on. Okay, so we will have 1 into 2 power 0 plus 0 into 2 power 1 plus 1 into 2 power 2. Okay, then let's take care of the values that are after the decimal point. So we have 1 into 2 power -1 plus 0 into 2 power -2 plus 1 into 2 power -3. Okay, then we have 1 plus 0 plus 4 plus 0.5, that is 2 power -1, that is 1/2, that's 0.5 in decimal, plus 0 plus 2 power -3 is 1/8, and that translates to 0.125. Okay, so we have 5.625 base 10 as the answer. Okay, okay, so let's try this question. So we are given an equation, 7526 base 8, it's an octal number, minus y8 is equal to 4364 base 8. So we have to find out what is y. Okay, and the representation is stated like this: xn, where x like it stands for x to the base n. Okay, so let me rearrange this equation a bit. And after solving this particular question, I'll take the doubts. So whatever doubts you have, you can put it in the chat box. And yeah, you can put it in the, you can put your doubts in the chat box. I'll respond to that. Okay, so observe this particular point. So now we need to subtract 2 from 6, sorry, subtract 6 from 2. Okay, but we are not going to carry 1 here. Okay, because here the base is 8. Okay, so what we need to do is we need to borrow 8 instead. Okay, so I will give an equivalent example in the decimal system as well, so as to make this particular concept clear, because we have a habit of borrowing 1 without understanding why it is being borrowed, right? So observe this particular thing. So what we need to do is we borrow 8. It means whatever is the value, we need to add 8 into that. Okay, So we have 2 minus 6, right? And we need to borrow 8. So this value will be minus 4 plus 8, that will be 4. Okay, so this is 4. Fine. And as we have borrowed, so we'll represent it as 1 here. So this particular one needs to be subtracted from this 5, 3 wala column. Okay, so it will be 5 minus 3 minus 1. Okay, so this will be 5 minus 3 is 2, minus 1 is 1. Okay, then 7, 4, 3. So the answer is 3142. Okay, so now let me show a decimal equivalent of that. Let us say we have a number 25 minus 17. Okay, so what we tend to do is we directly just mention here as 15 and we cut this one as 1. But how did this particular 15 come up? Okay, so what we are doing is whatever is the base of the number, we are adding it to these operands. Okay, so let's say earlier we wanted to do 5 minus 7, but as 5 is less than 7, so what we do is, so this is in decimal, right? So the base is 10, so we actually add 10 to it. Okay, now we have 15 minus 7, that is 8. So we represent 8 here, and exactly the same thing we are doing here as well. Okay, so this is for octal. So similarly, if the question is asked for hexadecimal, then we need to add 16 for hex. Okay, yeah, so as I mentioned, so if anyone has a doubt at this point, they can just let me know. Is my screen visible? Okay. Yeah, actually I'm having some internet issues. So. Okay, so does anyone have any doubt? Okay, I see a few questions. Will the answer be 0 so that it will be okay? You got that 5. Okay, does anyone have any doubt? So far whatever problems we have solved, so does anyone have any doubt in that? Is the recording available after 5 o'clock? Yeah, so it will be available. Basically we have a YouTube channel, so on that channel these recordings will be available, and NPTEL team will share that link with you. And yeah, right after this session I will be uploading this recording, and I will also upload the slides. Okay, so one question is one example on 3 to 5 base conversion. Okay, YouTube channel name is PMRF TA Arpit Bal. Yeah. Okay. And yeah. Okay. Yeah, do you have a doubt? Luck. Yeah, YouTube channel name is PMRF TA Arpit Bal. So the links will be shared with you, so don't worry about that from now. Okay, fine. So then we can proceed to the next question. Okay, so we have this number in decimal, and we need to get a base 4 number system. Okay, there is another question. 3 to 5 base conversion. Yeah, for 3 to 5 base conversion, what you can do is you can again like you can convert it to decimal, and then you can convert it using the long division method. Okay, that should be the straightforward one. So any base is given, you can do that. Otherwise you can also try the bit grouping technique. It will only work for like anything which has a 2 to the power n wala concept. Okay, so let's continue with this problem. So we are given this number 225.4375 in decimal, and we have to convert it in base 4 number system. Okay, so if we have to convert it in base 4 number system, then we again need to do the long division method for the integral part. Okay, and for the decimal part, what we need to do is we need to do a sort of multiplication. Okay, so let us separate it out. So we have 225 as the integer part, and the fractional part is 0.4375. Okay, so let's perform the long division with the integer part first. So we will have 4 into 56, so it will be 224, and the remainder will be 1. Okay, so again dividing it by 4, so 4 1 is 4, 16, so it will be 1 4 4 16. Yeah, this is correct. So we won't have a remainder here, and we again divide with 4, then we will have 3, and the remainder will be 2. Okay, so as we see, 3 is less than 4, so we will stop here. So now what we can do is we need to proceed backwards, so it will be 3201. Okay, so 3201 is the integer part. So now the question is what to do for the fractional part, or the part which is after the decimal. Okay, so for the part that is after the decimal, what we will do is, instead of doing long division, we will start multiplying it with the base, whatever is the base, 4. So 0.4375 into 4. Okay, so let us do that. It will be 20, 0 to 28, 30, sorry, 03. This will be 12, 15, 17, 1. Okay, so we will have it as 1.7500. Okay, so here after, okay, so you have to do long division when you are dealing with the conversion related to the integer part of the number, and you have to perform this multiplication when you are taking care of the post decimal part of the number. Okay, so yeah, so and you can see it here itself, right? So whatever this number was given, what I did is I separated the integer part and I separated the post decimal part. Okay, the integer part, I performed long division on that and obtained the integer result. Okay, so this is in the base 4 number system, and similarly for the post decimal part, what I do is I multiply it by 4 first. Okay, then whatever is the result obtained after multiplication with 4, so whatever is present before the decimal, so before the decimal, in our case 1 is present. Okay, so this is something we need to store. Then what we will do is we will take the post decimal part of the result. Okay, so 0.7500, and we will again multiply it with the base. So we have 0 0, this is 20 0, this is again, this is 3.000. So this is the pre-decimal part. that is the integer part of this result. So in long division, what we used to do, whatever was the remainder, we used to traverse backwards till the first, right? But for the decimal part, where we are performing the multiplication, so whatever value is obtained first, that has to be represented first. Okay, so let us see how it happens. Give me a moment, I'll admit the other students as well, some are waiting. Yeah, okay. So from the long division method, we have 3 2 0 1. So the last remainder that we obtained, that will come first here, then the next one, then the next one, then the next one. And for the post decimal part, what we do is, whatever is obtained first, that will be presented first here. Okay, so 1 was the first value that was obtained after our uh, multiplication with 4. Then the next one was 3. Okay, and okay, so you will ask me that, so when do we know when to terminate the repeated multiplication, right? So we usually terminate the repeated multiplication when the entire decimal part, the post decimal part, goes all 0. And here you can observe that the entire post decimal part is all 0, right? So this is the last value that we need. So 3201.13 is our answer. That is option B. Okay, does anyone have any question in this one? Okay, Nadesh, your doubt is clear? Okay. Okay, then we'll proceed with the next question. Okay, so now what we need to do is, we need to find the ones complement of 01101. Okay, so for the ones complement, the trick is you just flip the bits. Okay, so for 0 it is 1, for 1 it is 0 0, for 0 it is 1, for 1 it is again 0. So 1 0 0 1 0, option C. This was an easy question. Okay, so then okay, so let me go by the logic. How does this happen? So for any okay, so for taking the ones complement, what we need to do is there a way to do ones and twos complement in other number systems as well? Yeah, so in other number systems it is called as n plus 1's complement and n's complement, or n's complement and n minus 1's complement. Okay, so because it is binary representation, so here n is 2, so we will have 2's complement, and n minus 1 will be 2 minus 1, that is 1, so 1's complement. So similarly, let's say we have a decimal number. Okay, so in decimal number system we have the base as 10, so n's complement will be 10's complement, and n minus 1's complement will be 9's complement. Does that answer your query? Okay. Okay, so similarly, let's say this is an n-bit number, so there are total 5 bits. Okay, and we want to get the ones complement using the logical approach, right? So 5 bits means, so 2 to the power 5 equals to 32. Okay, so 32, and so this is the n's complement. To get the n minus 1's complement, what we need to do is we subtract minus 1. Okay, so after subtracting minus 1 we will have 31. So what is the decimal equivalent of 31? Okay, this is 16 Oh, sorry. Yeah, I made a mistake. Sorry. Okay. So this is where it will end. Yeah, I made a mistake here. Instead of it should be 15. Okay, so we will have 1 1 1 1 1. Okay. Yeah, and whatever now. Okay, just a minute. Let me admit others. Yeah, and whatever number is given to us to find the ones complement, what we need to do is we need to subtract that number from this particular number. Okay, so if we perform the subtraction, we can see this is 0, this is 1, this is 0 0, this is 1. So this is same as the ones complement, but by observation we can see that by observation we can see that whatever number is present here, to get the answer we just need to flip the bits. And this is the trick that we actually use regularly, but this is the logic behind it, that whatever is the number, you take the n's complement first, then you get the n minus 1's complement, and then you subtract that thing from the given value to obtain the n minus 1's complement. Okay. So moving on to the next question. Okay, so 8-bit 2's complement form of minus 45 base 10 is. Okay, so let us find out what is the decimal form, sorry, what is the binary form of 45. We have there will be a remainder of 1, then we have 11. Okay, so the binary value is 101101. Okay, and what we need to do now is we need to find out the 8-bit 2's complement form of this particular number. As I mentioned earlier, so if a particular representation is given that this number needs to be in n bits, but the answer that you have currently is falling short of n bits, what you can do is you can append zeros to make it that n bit number. So here we can see that it is actually a 6-bit number. Okay, and this 6-bit number, it needs to be converted into an 8-bit number first before getting the 2's complement form. Okay, so what we will do is we will append 2 zeros. Okay, so this is our number 00101 that is 45 in 8-bit representation. So now we need to get the 2's complement form of this number. So for getting the 2's complement form, what we will do is first we will get the 1's complement, then we will add 1 to it. Okay, so we will take the 1's complement of this number, so that is basically flipping the bits 110 100 10. Okay, this is the 1's complement, then for 2's complement we add 1, that is 1100 10 1. Okay, so the answer is option B. Fine. So now let us move to the next question. Yeah, okay. So now we have a question that we need to perform addition in like we have to perform hexadecimal additions. So we have two hexadecimal numbers that is given to us, and we have to report the result in hexadecimal format itself. So here what you can do is maybe you can convert these hexadecimal numbers into binary or decimal, whichever you are comfortable in, and then perform the addition and then get the answer and then convert it into hexadecimal, but that is going to be a bit cumbersome. So now I will show you a trick that you can use to directly perform this computation. What you can do is, so the first thing is you mention the hexadecimal numbers. Okay, so 0 1 2 3 4 5 6 7 8 9. Instead of 10 you write A B C D E F. Okay, so what are the two numbers that we need to add? This is DEF dot 12, then FE to 1. Okay, these are the two numbers for which we need to perform addition. Okay, so here it is 0, so this is straightforward. Okay, but now comes C plus 1. So here what we need to do is, so let us say whatever is your value. Okay, so let us say we are at C, we need to add 1. It means we need to move to the right by 1 step. Okay, so this will be D. Fine. Now F plus F. Okay, so now you need to figure out how many steps. Yeah, you need to figure out how many steps you need to move to the right of F to arrive at the result. Okay, so basically F is nothing but, okay, so let us start from F. Okay, if we move 1 step we are here, if we move 2 step here, 3 4 5 6 7 8 9, A B C D E F, right? So F plus F should be E along with the carry. Okay, so once you start your counting from the 0, then what we do is we increment this value. So as we have moved from F once, then what we need to do is we just mention 1, and the value at which we arrive is actually the lower bit. So E is here and we will put 1 as a carry. Okay, now we need to do the same thing for the E plus 1. Okay, we start from E, okay, and move to the right. Okay, 1 2 3 4 5 6 7 8 9. Yeah, 1 2 3 4 5 6 7 8 9, A B C D E, and then there is also a plus 1, so we arrive at D. Okay, so here we will have D, and because we moved around by 1 time, so it will be 1D and 1 will be in carry. Okay, so now let us start from D, move 2 steps to the right, 1 2. Okay, but there is a carry that is coming from the previous addition, so we land up at 0. Okay, So we will have a value of 1 0 actually. 0 is here and 1 goes to the carry for the next computation. So 1 plus 1 is 2. Okay, so the final value that we arrive at is 20 DE dot D2. That is the representation in hexadecimal. Okay, does anyone have any doubt in this question? Clear. Okay, Debadrita has a doubt. When I add this hexadecimals, I got f1d.d2 as an answer. No, f1d.d2 won't be the answer. The answer is 20de.d2. So maybe you can recalculate it once, or else what you can do is you can also convert these numbers into decimal first. Okay, that will be a long method, but if you are comfortable with that, you can use that one as well. You convert def.12 into decimal. Similarly, you convert 12ef.c into decimal. You perform the normal decimal addition, and then you observe whatever is the result. But then the problem is again, like once you have it in decimal, you need to convert it back into hexadecimal to arrive at your answer, right? So maybe you can try that just as an experiment to check whether your answers are matching or not. Okay, that's fine. So is there any other doubt in this particular question? Okay, yeah, sure. So should I explain this question 14, Rashmi? Okay, yeah. So what we want to do is we need to perform hexadecimal addition of these two given numbers. Okay, but unlike the normal addition, let's say we are doing 2 plus 3. So when we add d plus e, we become a bit uncomfortable, right? So instead, what we will do is we will use this something similar to a number line. We will represent all the hexadecimal numbers that are present here. Okay, and we will count it in terms of the hexadecimal numbers itself. Like we will count 1 2 3 4 5 6 7 8 9. Instead of 10 we will say A, instead of 11 we will say B, so on and so forth. Okay, so let us take this particular example of FF. Okay, so it means you will start from F. Okay, and you have to move F directions towards the right. Okay, so if I move once towards the right after crossing F, what I need to do is I need to put a 1 here. It means once I am turning over towards the 0 part again. Okay, so yeah, we have to move towards the right by F number of steps. So if I go 1 step, I'll land up at 0. If I go 2 step, I'll land up at 1. 3 step at 2, 4 step at 3, 5 step at 4, 6 step at 5, 7, 8, 9, 10 step here. Similarly, if I go on A step at B, B step at C, and similarly Fth step will be at E. Okay, so we will have 1 E as the result of F plus F. So 1 will be actually carried to the next computation, and E will go as the answer to the final. Does that clarify things, Rashmi? And similarly you perform for the remaining of the digits, and that is where you have the final answer. Okay, so is there any other question? Okay, if not, then let's move to the next question. Okay, so here what we need to find out is we are given a decimal number minus 28. We need to find the 2's complement representation. We need to find out the 16-bit 2's complement representation. Fine. So what we need to do is, first we need to find out the binary representation of 28. Okay, so for that we will perform long division method. This will be 14, this will be 7, okay. So yeah, so we have 11100. So this is the value of 28. But what we need to do is, it has been mentioned in the question that it has to be a 16-bit representation. But here we have only 1, 2, 3, 4, 5. So we have only 5 bits. So rest what we can do is we can append 0 so as to make it a 16-bit number. Okay, so this is 4-bit. 1, 2, 3. So now it is an 8-bit number. So we need to add 8 more zeros. Okay, so now this is our 16-bit representation of 28. Now what we need to do is we need to find out the 2's complement form. So for finding out the 2's complement form, the first thing that we need to do is find out the 1's complement of this particular number. For finding out the 1's complement, we just need to complement the bits. Okay, so it will be 1 1 1 1 1 1 1 1 1 1 1 0 0 0 1 1. So this is the 1's complement of 16-bit representation of 28. Okay, now to get the 2's complement, we just add a 1 here. Okay, now we have 0 1, this will be 0, this will be 1 0 0 3 4. Okay, so it is, we can see that this is the final result which represents minus 28. Okay, so this is basically our option C. Okay, yeah, so now I'll open the forum for any doubts if anyone has. So either they can post it in the chat box or maybe they can raise their hands. Okay, so these were the numerical practice problems that I had planned to discuss with you. So I hope that this session was helpful for you, and it will be helpful for you for solving the problems that come in the assignment as well as in the exams. And so we will have these sessions regularly every Saturday from 3 to 5. The lecture videos as well as the slides, they will be shared by the NPTEL team. The videos will be uploaded in uploaded on YouTube, on my YouTube channel. The link for that will also be shared by the NPTEL team. It will be shared by the NPTEL team, Maria. Yeah. So yeah, Ankit, these questions will be available just after the sessions end. So NPTEL team will share both the links to the question as well as the YouTube channel where this session's recording will be shared. So this session is being recorded currently. Okay, so can you explain question 7 again? Question 7. Yeah, I'll explain question 7. Okay. 1's complement is equals to 9's complement if we take the same number. Sorry, I didn't get your doubt. Can you elaborate it a bit, Keshav? For example, 0, 1. Okay. Yeah, exactly. Yes. I understood your point. Yeah. So because this is basically it's a similar form of representation, means you will have the same value, like you are just translating it into from one number system to another, right? So at the end of the day the values will be same, right? So yeah. Okay, let me explain the question 7 part again. Yeah, so here the question 7, it demands that we need to find out the sum of these two given numbers, minus 1010 and minus 0101. So what we need to do is, minus 1010 is actually representing minus 10 and minus 0101 is representing minus 5. We first okay yeah we first need to put it in a 5-bit format, just like the last example that we saw, right? We needed a 16-bit representation but we were falling short of bits. So what we did is we appended zeros to that particular number. Like let us say I have 98, right? 98 in decimal, and if I append a 0 to the left of this thing, the value of this particular number, it stays the same, right? So the same thing, if I have a number 10 in binary, so it represents 2 in decimal, right? And if I append a 0 to the left of it, the value of this number doesn't change, right? So similarly, 1010 is a 4-bit representation. To convert it into a 5-bit representation, what I do is I append a 0 before it. Okay, so here that appending happens, and the same thing I do for the 0101 as well. I just append a 0, so I have 0010. Okay, after I have these magnitudes, I want to represent it in 1's complement form. So for 1's complement form, whatever digits you have, you just flip the bits. If it is 1, you convert it into 0. If it is 0, you convert it into 1. Okay, so that's what I have done here. Okay, then it is basically addition. So I add these numbers, whatever result is obtained, if there is a carry, what I do is I take that carry and add it to the main number that is present in the square bracket here, the square box here. Okay, and then I add plus 1 to it. Okay, after addition of plus 1, so after addition of plus 1, there's a 1 that appears at the output of the answer, which means that the result is a negative. The result has to be a negative, right? Minus 10 minus plus minus 5, it has to be minus 15, right? So this one represents that the result is negative, and then the remaining bits, these will represent the magnitude of the answer. Okay, so it is again, it is like minus 1111. Fine. So if you convert 1111 into decimal, you observe that it is nothing but 15. So the answer that you have written is minus 15. Does that answer your question, Harsh? I mean, you can practice as many problems as possible, and during the lectures also. So what I will suggest is, if there is a if there is an example problem, then try to do it on your own before looking at the solution, and then only move to the solution. So that will be more beneficial for you instead of directly going through the solution. So I'll suggest learning it in an active way rather than just passively trying to understand the concepts. And whatever sums we have covered till this point, so you can practice them again once you have the links available with you. So what you can do is you can just pause the video, see the question, try to do them by yourself, and if you have any doubt, what you can do is you can use the forum to post the questions. So you have a discussion forum that is available on the NPTEL website. Okay, you can post your doubts there, and I will try to resolve that. Okay. Is there any other doubt? Yeah, Keshav. Above text. Okay, I'll discuss this later. Is there any other doubt? Related to today's session, or any concept that I covered that you want me to repeat again? Okay, then let me just summarize through whatever we have discussed. All classes will be on Saturdays and Sundays. I think there is a class on Friday as well. So for this, my session is on Saturday from 3 p.m. to 5 p.m. Other TAs will be taking the other sessions. So yeah, I guess tomorrow you have a slot. I think in the NPTEL announcement section this has been announced. You can recheck it once again. And I guess there's a Friday session and a Tuesday session. So those sessions will be taken by other TAs. My session is every Saturday from 3 p.m. to 5 p.m. Okay. Now let us just give a look at what we solved today. So the first question was related to getting the decimal equivalent of the number. So this was one concept. Then the next thing that we solved today, it was related to means we have a decimal number and we need to get the hexadecimal of that. So interconversion between the number systems. Then from decimal to binary. Then we tried to find out the octal equivalent and the shortcuts, like instead of directly just converting it to other form, we learned that we can group them into bits of 4 for hexadecimal and bits of 3 for octal. Then we also saw it's a similar concept to the previous one, then that how can we get the binary to octal representation. Next was what will be the maximum number of bits at the output of the solution. Then next was ones complement addition. So you are given two numbers and you need to do the ones complement addition of these two numbers. Then if you have a number in a given base, how to find out what is the base of that number provided the equivalent representation of that number in a different base is given. Then we learnt if there is a decimal involved, how to solve that particular problem. That if anything is to the right of the decimal, then we start with taking a -1, from -1, -2, -3 and so on to the right of the decimal. To the left of the decimal we start with 0, 1, 2 and so on. Then we also solved a very simple equation that is present on the screen. Then the next question, it was basically converting from one number system to the another number system, that is from decimal to the base 4 number system. And we also saw that if anything is present after the decimal, so how to convert that into that particular base. So for anything that is present before the decimal, what we used to do is we perform the long division. Similarly, for anything that is present after the decimal, we perform something like multiplication, right? And after multiplication, in the long division case, what we used to do is we take the reminders from bottom to up, and in the multiplication case, what we do is we take the first thing that is available with us as the first digit. Like here 1 was available, we took 1. Here 3 was available, we took 3 after the 1. Okay. Similarly, this was a simple one. We just needed to find out the ones complement of this particular number. Then we found out what was the 8-bit 2's complement form of 45 minus 45. Then we saw how can we perform addition in a different number system instead of going back to decimal and then performing the addition and then going back to that particular number system. So we saw this number line approach. Then we performed this 16-bit representation of 2's complement of a particular number. Okay, so that's all for today's session. So I'll stay here for some time. If you guys have a doubt, please feel free to let me know. Okay. If you don't have any doubt, you can leave the session. Yeah, and the slides and the video, it will be available, so the NPTEL team will share that, so no need to worry about that. Does anyone have any doubt? For digital circuit, what you can do is you can refer to the slides that sir has shared. In addition to that, if you want to read more, then during my bachelor's I used to have Morris Manno digital circuits for basic digital electronics. That should work fine. Okay, 2's complement of 45 is, yeah, so the thing that we solved, it was for minus 45. Yeah, so this complement representation is especially useful for representing negative numbers. We have, why there is a need for different number systems like hexa, binary, octal. Okay, it can be for different reasons, like maybe there are different machines which understand only binary. Okay, the computer at the lowest level, it understands binary, so that's why we need this binary number system. And but the human understandable one is the decimal one, so for that purpose we need uh, decimal. And regarding hexadecimal, so if you have played around with microcontrollers and microprocessor, the basic ones, 8051 and those things, so it takes hexadecimal and those things as the input. Yeah, there can be a various purpose for this, having a different sort of number system. Yeah, so is there any question, any more question, any doubts related to this session or the next one? Okay, that's great. Okay, thank you everyone for joining this session. I hope it was useful for you. There is no such attendance policy as far as I know. So, so these sessions are meant to be for your benefits. Like you can get to practice the problems that are being solved here, and you can clarify the doubts which you have here. Okay, thank you everyone for joining. So I'll be ending the session now.